So, the hook for today is a problem that I would not expect you to try to do. I just want you to appreciate the sort of problem that I'm going to give you techniques for solving. So by the end of this lecture, you should be able to do such a problem. And you might feel like you could do such a problem now. That you feel like it, you could try to take that on. But I think you will find it much easier to do the problem, and you will be much more confident that you have gotten the right answer when you are done if you learn these techniques for working with relative motion problems. And again, you may be resistive. That's gimmicky. I don't like that. I don't need that. And the time will come when you will need it, and you ought to trust me. Please learn this technique. So you're given a problem like this, that the person walks at this speed relative to the surface that they're walking on. I had to figure that out. And you have the surface that you're walking on is going west. And what will your resultant movement? That is, how will you move relative to the earth, not relative to the walkway, which is this here. So first you recognize it as a relative motion problem. And then I would like you to take it on as follows. But again, let me reiterate, I have made this problem as easy as possible. This one, unlike that one, I think you could look at it and you could figure out the answer and be pretty confident. I wanted it that way. I want you to see that my gimmick yields the same result as what you know the right answer should be. So please don't take the ease of the problem I have given you to indicate this is useless, unneeded stuff. So first I take this piece of information, 2 meters per second east, and that I recognize as the velocity of the person relative to the walkway. And there is your first gimmick, pulling the information with this paired subscript, something relative to something else. The letters you choose are completely up to you. Hopefully they make sense to you. It's nice if they could make sense to your reader as well. Okay, and then we have the walkway going to the west at 5. And so I say the velocity of walkway relative to the earth is 5 to the west. And then, as in all problem solving, the most important piece of information you can take from the problem statement is where you're trying to go with it. What will your result? What do they mean by that? And I take that to mean what will be the velocity of the person relative to the earth. There's the problem solving, is my taking this ambiguity here and giving meaning to it. All right. Now, having pulled all the information with this subscript form, then you take the one piece of information where you don't know anything about direction. It's going to be much more tricky if there are multiple ones you don't know anything about direction, and I doubt I would give you anything like that except for extra credit possibly. So the one whose direction you don't know, because you don't know how to draw that vector, that's the one you ought to be solving for. So to the left of the equality, I put this one whose direction I didn't know. And then to the right of the equality, I take the first subscript here, and that has to be the initial subscript, and the last subscript there, and that has to be the last subscript. And there could be a whole string of these, and for each one of these, they should be paired up so that the second subscript here is the first subscript on its following pair. And then maybe maybe they also told you how the earth was moving relative to the sun. So you had the velocity of Earth to Sun, ES, and they wanted to know how the person was moving relative to the Sun. Then I would have out here, I'll write it, gold darn it. I would have the velocity of the Earth relative to the Sun. And this whole thing here would add up to the velocity of the person relative to the Sun. Okay. Okay. Get rid of that. And hopefully get rid, no, I'm not, oh, there we go. Okay. So, and this is the gimmick, but it is so valuable. And then you just do what this sentence says. You take this vector, P to W. That's 2 to the east. And you draw that vector. And then you add on to it, as it says, VWE. Okay. And when you add vectors, you of course add them head to tail. And if you add those two head to tail, the resultant, which goes from the tail of the first to the head of the last, is equal to this. So there you are, that the velocity of the person relative to the Earth is going to be 3 to the west. It was easy. You didn't need that, but I needed to illustrate in an easy context what we're going to be doing. Okay, now a little bit more legitimate problem. And if you feel like you can do it, please try to just make an attempt. Get your brain so engaged that you're going to start learning. So without looking back at the previous slide, C1, you would recognize this as a relative motion problem. So you pull the information with appropriate subscripts. I hope you're stopping the show so that you can do it yourself, and then starting again when you need my help. Okay, so hopefully that's what you got for all the information. And then, oh yeah, you look at the one whose direction you don't know, put it to the left of the equality, and then you do what it says to do. You take the MC, which is 4 to the east, and then you add on to it VCE, which is 10 to the north, and what this says is that when you added those two, the resultant is VME, which we were trying to find. So this vector is the answer. The length of that vector, which you could get with a nice Pythagoras, is the magnitude, and the direction of the vector. And remember, you want to find the direction at the tail end. You could find this angle, how many degrees east of north, or you could find this angle, how many degrees north of east, and it should be a simple trig task for you to get what that angle is, and then you write the answer and you're done with the problem. Now, this is 3 on your worksheet. A stick floats north in a river at 12 meters per second, and you ought to recognize that what they're doing with that stick is telling you how fast the water is moving. It's just hard to see how the water moves, so a stick which moves with the water is very useful. So the stick, the bug on the stick, and the water all are going north at 12 meters per second as viewed by this person on the shore. And the question is, what does it look like to the bug on the stick, who, like all creatures, thinks that it is in the center of the universe, and so it is sitting still while this person on the shore moves past. And what would be the velocity of that person relative, and hence the shore, relative to the bug? So VWS is 12 to the north, the velocity of the water relative to the shore, 12 to the north, the velocity of the shore relative to the water. That's going to be negative 12 to the north, or more elegantly stated, 12 to the south. The point being, when you switch the order of the subscripts, you switch the direction of the vector. Okay? And that, of course, is going to be applied in this problem, which you ought to do, only starting the show again as often as you need a prompt from me. And I presume you have finished, or you need a prompt from me. We recognize it as a relative motion problem. We first pull all the information in that subscript form, and then we take the one whose direction we don't know and put it on the left, and that completely dictates we got to start with a W, WB. And then B has to be matched with B, and we have to end with a G. It's lovely. So nice. Okay? And then, of course, you would take this, which, I don't have any vectors here ready to go, so you're completely on your own. But remember, this first vector that you're drawing here would be 12 to the south. And then you would add on to it 5 to the north, and that would get you this answer. That's not so bad, is it? Okay, this problem doesn't come with a story, but all the information has already been pulled in that subscript form, and point out to you that this time the one whose direction we don't know is this one here. And that's all I asked you to find, was that direction. It would be possible for you to get the magnitude of this one here, but you definitely would not want to put VCB to the left of the decimal. You want to put VAC to the left of the decimal. And then you do what it says. And people, try to do it. I'm going to pull it onto the screen, but you try to do it before you see me. So first you have VAB, which is 10.1 to the west. And then you have this one, whose magnitude I don't know, but I know that it is going south. I don't know how long to make that vector. That's okay. What I do know is when I add these two, this hypotenuse, whose direction I now can figure out, whose magnitude I do know, is going to be what those two add up to. And now you have a nice right triangle, you have the adjacent and the hypotenuse. I think you could very easily get this direction of the AC. Before you try problem 6, a note. When the words bearing or heading or their equivalent are used in the statement of a problem, it means the direction relative to the fluid. So if you talk about the bearing of an airplane, that means its direction relative to the air. And the heading of a boat, that's its direction relative to the water. And so on. So here it is, a boat moves so relative to water, water moves so relative to what? Yeah, you can figure it out. And the boat must be directed. So they're asking for the heading or the bearing. And so you know what subscripts to use for that. It's relative to the water. How should the boat be directed? Go directly east. And it says how should it be directed, and then reiterate what should the boat's heading be. So those are both saying the same thing. But I know that the motion is going to be directly east of boat relative to water. Okay, you finish that out. Thank you.